तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So let us begin where we left off last time, and I would like to do a couple of examples today to put things in proper framework. Recall that we looked at the 2D isotropic oscillator, and let us quickly recapitulate what we had here. This H was equal to 1/2 P1 squared plus Q1 squared plus P2 squared plus Q2 squared in units in which the mass is equal to 1, the frequency equal to 1. I have chosen those units, and this was our Hamiltonian. Okay. Now this problem is integrable, the reason being that a constant F1, which is essentially P1 squared plus Q2 squared, and another constant of the motion F2 P2 squared plus Q2 squared are in involution with each other. It is a 2 degree of freedom system, and therefore the problem is completely integrable. We could go to action angle variables and so on, and we also discovered that since the frequencies are the same, the motion is periodic, period 1 in this case or whatever, and we know that the motion lies on a torus, and it is not ergodic on the torus because the trajectory is in fact just a closed curve, simple closed curve on this torus. Now the symmetry of this Hamiltonian system, the dynamical symmetry I pointed out, would be that set of transformations of the 4 phase space variables which would leave the equations of motion unchanged, and which would therefore take the solution set to the solution set itself. That symmetry involved a certain set of generators. It is a symmetry group of transformations, and the statement we made was that since this is a 2 degree of freedom system, n equal to 2, the symplectic group SP4, the symplectic group of 4 by 4 matrices, is isomorphic to the group of canonical transformations of this Hamiltonian, and the intersection of this group, or rather the subgroup of this group, which leaves the equation, the Hamiltonian, unchanged, is in fact the subgroup, the group that leaves this form unchanged, and that is the set of rotations in 4 dimensional space because there are 4 variables. So while SP4 is the group of CTs for this Hamiltonian, SO4, the symmetry group of this Hamiltonian, and the dynamical symmetry group of this problem is the subgroup of the symplectic group which leaves the group of canonical transformations which also leave the Hamiltonian unchanged, and that group I said was SU2, the dynamical symmetry of this Hamiltonian. And this symmetry group, the abstract group, is a group of 2 by 2 matrices which are unitary with complex entries and which have unit modulus. Now let me say a few words about SU2 separately here. SU2, it consists of all 2 by 2 matrices A, B, C, D such that so if this is a matrix M, such that M dagger M equal to, that is what is meant by unitary, all matrices which satisfy m dagger m equal to 1, and the S for the SU2 stands for the fact that determinant m equal to plus 1. If you put in these conditions, then you get the general group general matrix belonging to this group SU2. Now what we have to do is to do some counting of parameters. How many parameters are there, real parameters are there in a general 2 by 2 matrix? 8 of them, because each entry can be a complex number, so there are 8 parameters. Now we have to reduce that. Once you say the matrix is unitary, there is a certain set of conditions, and you have to impose all those conditions, and how many conditions would there be? By the way, this thing says m dagger equal to m inverse, so you have to find the inverse, and then you have to put the determinant equal to 1, and then you start imposing these conditions. And when you do that, it turns out that 4 conditions obtain the moment you say m dagger m equal to I, that gives 4 conditions, 1 for each element out here, and therefore the number of parameters is reduced from 8 to 4, and then you say the determinant must be plus 1, so 1 more parameter is gone and the number of independent parameters is just 3. I leave it as an exercise to you to show that the general element can be written as some number alpha beta minus beta star alpha star. So you can write a general member of this group of 2 by 2 matrices SU2, the SU2 group, in the form of some complex number alpha, some complex number beta, and then minus beta star and alpha star, such that mod alpha squared plus mod beta squared equal to 1. We can always do that. Now what sort of parameter space do you have? You can ask, what is the parameter space of this group? The space of this group is all numbers alpha and beta such that mod alpha squared plus mod beta squared is 1, and of course you could also say that if alpha is equal to alpha 1 plus I alpha 2 and beta is beta 1 plus I beta 2, then this can be written as alpha 1 squared plus alpha 2 squared equal to 1. So we have 4 real numbers alpha 1 through beta 2 such that the sum of the squares of these 4 real numbers equal to 1. What kind of object is that in this 4-dimensional space? It is the surface of a unit sphere in the 4-dimensional space. So one says that the parameter space of SU2, the parameter space is the surface of a sphere in 4-dimensional space. It is denoted by S3, a sphere of a 3-dimensional sphere S3. S1 is just a circle, S2 is what you are used to as the surface of a balloon in 3 dimensions, a 2-dimensional sphere. A 3-dimensional sphere is the surface of a unit sphere embedded in 4 Euclidean dimensions, and so on. So this provides a great deal of simplification. We will not get into that right now, but I want to point out that this is a symmetric group of this Hamiltonian, it is non-trivial. Now you could ask, every group is generated by some generators of transformations. What generates this group here? It turns out that the constants of the motion I wrote down earlier, namely J1 is 1/4 q1 squared plus p1 squared minus q2 squared minus p2 squared, J2 equal to 1/2 q1 q2 plus p1 p2, and J3 is 1/2 q1 p2. These 3 quantities, these 3 functions of the phase space variables are constants of the motion, but they are not in involution with each other, and they turn out to be the generator of the group SU2, of the dynamical symmetry group. You need 3 parameters for that group and there are 3 generators. So these turn out to be the generators. Later, if time permits in this course, I will talk a little bit about generators of Lie groups and so on, but right now I want to go ahead and incidentally verify that Ji Jj is equal to epsilon ijk jk. This means the Poisson bracket of J1 with J2 is J3 and in cyclic permutation. So they are not in involution, of course, and they are not all independent, because in this problem how many independent constants of the motion can you have which are time independent constants of the motion? Well, the phase space is 4 dimensional, so you could at best have 3, at best you could have 3, but it is integrable, therefore you really have 2 constants of the motion independent which are in involution with each other, but you can have more constants of the motion, you can have a large number, you have F1, F2, this is F1 minus F2, so it is not independent, then you have F3 and then you have F4. So you really have a fairly large number of 4 constants of the motion, all of them are time independent, but they cannot all be independent of each other. So discovering this is not a trivial task, it is trivial in this problem but it is not true in general. Finding what the symmetry group of a Hamiltonian system is, finding how to integrate it, how to find the symmetry group is non-trivial. So let us go from here to a real problem. This was a 2-dimensional oscillator which would be a model in many physical situations, but let us go to a real problem, the problem of a planet moving around the sun, the Kepler problem, and let us see what happens there. I should mention, by the way, just as a matter of mention, the 3-dimensional isotropic oscillator in 3D would mean this. What would this be replaced by? SP6. What would this be replaced by? SO6, because there are 6 of these guys, and you could ask what is this going to be replaced by? It turns out it is replaced by 3. How many generators would SU3 have? No. So what you have to ask is how many parameters, independent parameters, does an n by n unitary matrix have, and then you must subtract 1 from it for the determinant equal to 1, and it is n squared. Un has n squared generators, the number of elements is 2n squared because there are n squared elements, each of them is complex, so there are 2n squared, but the number of independent parameters is only n squared for Un, the unitary matrices in n by n matrices, and then when you put the S condition, the S determinant equal to 1, it becomes n squared minus 1. So 3 squared minus 1 is 8, therefore SU3 has 8 generators. So there are 8 of these quantities, you have to discover 8 combinations, not these, but there are 8 of these combinations which would be invariant, which would be constants of the motion satisfying a certain algebra, namely the SU3 algebra. Okay. So that is not our immediate concern, yeah, yes, that is not our immediate concern, but let us look at the Kepler problem. Or the Coulomb potential. Once again, the Hamiltonian as a function of r and p is just p squared over 2m, that is the square of the kinetic energy, that is the kinetic energy, the square of the momentum over 2m, minus, let us assume that it is an attractive potential, although it does not matter, it could be attractive or repulsive, minus some constant with appropriate physical dimensions over r in spherical polar coordinates. a 1 over r potential leads to a 1 over r squared force once you differentiate it. Okay. So this is the central force here. Now we know in practice that the orbits, as Newton proved, are actually ellipses, but there are other orbits to this potential. You could also have a hyperbolic orbit, you could have a parabolic orbit, in fact they are conic sections always, and the motion in an elliptic, all bounded orbits are actually closed curves, they are periodic motion. That is very special to this potential. The moment I change this 1 over r and make it say 1 over r squared or 1 over r cubed or something like that, this property is gone, it is immediately lost. The only central potentials for which all the bounded orbits are closed curves, are periodic orbits, the only central potentials are in fact the 1 over r potential and the r squared potential corresponding to the isotropic 3-dimensional oscillator. These are the only two potentials. The oscillator has a symmetry group SU3, we just saw that. The question is, what is the symmetry group of this Hamiltonian, because it too is integrable, completely integrable. What are the constants of the motion that one can write? The Hamiltonian itself. What else? The angular momentum about the center of attraction, about the center of force, because this is a central potential, so certainly this. Okay. Of course the moment I say L is a constant of the motion, it means all the three components of it in any frame of reference are constants of the motion, L1, L2, L3. Now is this problem integrable? Yes, it is integrable. What are the three independent constants of the motion in involution with each other which tell you that it is integrable? Yeah, so the three independent ones are h, L squared, L dot n, any one component, you choose whatever you like, the component of the angular momentum in any arbitrary direction, the total angular momentum squared, and h. These are three independent constants of the motion and they are in involution with each other, so it is integrable. But we are actually finding more of them, there is L1, L2, L3 here, they are not in involution with each other. And remember the angular momentum algebra, Li Lj is epsilon ijk Lk. Are there any other constants of the motion? These would be the constants of the motion even if the potential were not 1 over r. Any central potential V of r would have this set of constants of the motion, but there is something very special about Kepler, about this problem, the 1 over r here, and that is the existence of further constants of the motion. There is another vector quantity A and it is called the Laplace Runge-Lenz vector. Okay. And it is defined as P cross L minus mk r over r. This is the definition. Okay. And the claim is that A is a constant of the motion. So we have to verify whether this is true or not, and then we interpret what this thing does and where it stands in relation to h and L. It is quite clear that it involves L, it involves P, the momentum P, it involves the coordinate r and so on, but it is a very strange combination of things which is supposed to be constant. Now let us verify if this is true. So let us do dA over dt, and we need some space, dA over dt equal to, I start differentiating this. Incidentally, if this is the potential, V of r is minus k over r with a minus sign. What is the force on this particle? What is that equal to? Minus the gradient, minus del V, and that is equal to what? well this minus kills that minus, but then if I differentiate 1 over r I get another minus sign, so it is minus k over r squared times the unit vector in the r direction. If I differentiate with respect to r and use the formula for the gradient in spherical polar coordinates, since there is no theta or phi dependence, the other two derivatives do not act, and this is it. It is more convenient to write this as minus k over r cubed r vector. So I do not want to fool around with this unit vector because that changes from point to point and I forget to differentiate it, so let us put this r. So what is dA over dt? The first term is dP over dt, but dP over dt is equal to the force immediately. So this is equal to minus k over r cubed r cross p L, but what is L in terms of, let us get rid of L and write everything in terms of r and p. So what is L? R cross p. So I have to keep track of this bracket, so let us do that, and then the next term is p cross dl over dt, but that is 0 because dl over dt is 0, L is a constant of the motion, and then the next term is minus mk, and I differentiate this, so you get an r squared and that becomes a plus dr over dt r, and then minus mk over r dr vector over dt. So this is the full time derivative of A, where we have used the fact that the force is given by a 1 over r squared force, we have used the fact that angular momentum is conserved, and we put in Newton's equation, dP over dt has been written equal to the force. Okay. So on the solution set where all these things are valid, this is what dA over dt is, and now we have to start simplifying. Now this term I can simplify right away, m dr over dt is just the momentum, so permit me to remove this m and write this as p here in this fashion, and what is this equal to? This is minus k over r cubed, and let us use the formula for the triple product, A cross B cross C. What is A cross B cross C? A dot C, so that is R dot P, A dot C P minus A dot B, that is R squared P. By the way, how do I know that A cross B cross C is A dot C B minus, pardon me, how do I know this? We are on our desert island, no information, so we have to start afresh. Well, we can always write it in components and do this, but let me give you a simple argument here, A cross B cross C equal to, now what can it possibly be? A, B, C are three arbitrary vectors in space, generally not collinear. Pardon me? It has got to be in the plane of B and C, because you could use these as oblique coordinates, it has got to be in the plane of B and C, very nice. So it is equal to some alpha times B plus beta times C. Anything in the plane of B and C can be expanded in terms of B and C linearly. Now what should alpha and beta be? What sort of object should alpha and beta be? Vectors, scalars? Scalars formed out of what? A, B and C, but the left hand side is linear in A, B, C, each of the vectors, therefore the right hand side must also be linear, therefore this guy cannot involve B, it must be formed from A and C. What are the possible vectors you can have, scalars you can have from A and C? You can have A dot C, you can have A squared, you can have C squared, but A squared and C squared are not linear, so you got to have A dot C. So this is A dot C, A dot C B, but nobody told you it is 1 times A dot C, it could be square root of 3 pi times this thing, so some lambda times A dot C, right, plus some other constant mu times again A dot B. See, it has got to be this, where lambda and mu are numbers real numbers and they can't depend on ABC, so they are universal numbers. For every ABC they must be the same numbers, right. Now what happens if you interchange B and C on the left hand side? You get a minus sign, therefore that must be true here too. Now how can that happen? One of them has to be minus the other, so this is the only way it can happen is a minus. That's it. Now what do you do next? You have used linearity, you have used homogeneity, and you have said the whole thing, they are linearly independent in 3 dimensions, so etc. So the only thing you can have is, yeah, put a special case. Now put a special case, yeah, put ijk, and then you discover lambda is -1. So the job is done. Okay, I leave you to find A cross B cross C cross D in the same way by doing this, but anyway, so we have successfully found this formula and we come back here. So you got this plus mk over r squared dr over dt r minus k over rp. Now is there any cancellation? This second term, this becomes plus k over rp and that is minus k over rp, so permit me to cancel this term against that term, and then you have this term here, this is equal to minus k over r cubed r dot p, but that is dr over dt, and then there is an m and then an r plus mk over r squared dr over dt r. What do I do with this? R dot dr over dt, that is d over dt of half d over dt of r squared, but r squared you write as little r squared and then it becomes r dr by dt, right. So you use this well known vector identity, u dot du over dt is always equal to u du over dt, because you can write each side as half the derivative of either u squared or u dot u. It's a very very useful identity, and then immediately you realize this is equal to r dr over dt, and you remove one of the r's, you get here, and this cancels that, equal to 0. So indeed this A is a constant of the motion, therefore it remains unchanged in both direction and magnitude. What is the direction of L? L is perpendicular to the plane of the orbit, because r and p define a plane and this plane is the same at all times, that is Kepler's second law, and then L is perpendicular to it. And what is the direction of A? It is also unchanged, so what is the direction of A? Well, you can see that what is going to happen is that if this is your orbit going in this fashion, the plane of the blackboard let us say is the plane of the orbit, then at any point this is the direction of r, this is the direction of p, so r cross p comes out of the board in this fashion, and that is the direction of the angular momentum perpendicular to this plane. Now this guy here is p cross L, there is a further p cross L and then there is an r, so in which direction is it? Well, you could find this at any point in the orbit, it is the same at all places, right. So for instance if you found it here at this point, this is r and that is p, so r cross p, the angular momentum comes out, and then you got to do an L cross p and that goes in here, and so does r with a minus sign, that guy also goes in here. So it is in the direction of the major axis, it is along the major axis of this ellipse, and now it says it does not change. So what does that imply for the ellipse? What does that imply for this orbit? It does not precess, otherwise the ellipse could precess very slowly, So you could have a motion of this kind, and this happens if you put a little perturbation. It would do this, it would no longer strictly be an ellipse, but it would precess slowly. That does not happen for the Kepler problem with a strict 1 over r potential, because the lens vector prevents it from doing so, the constancy of the lens vector, and it is in the direction of the semi major axis. Okay. Now I ask, yeah, P is m dr over dt, so there was an m here. Yeah, you check the dimensionality of these things. I have absorbed all lots of dimensions in this k here, k over r is dimensions of energy. Okay. Yeah.
What about the actual motion of the planet? Does it really go in an orbit ellipse, or just it goes like this way?
What is meant by actual motion?
How does it behave in space?
Which, I mean, the 1 over r problem or the an actual real planet, real life planet? What do you think? What do you think a real planet does? It certainly precesses, it certainly precesses. There are perturbations due to other planets. There is Jupiter sitting there, then there is tidal friction, there is tidal forces, there is a solar wind, there are lots and lots of other effects, many other perturbations, and then there is the general relativistic correction to the inverse square law of force itself, that too will cause a precession, a very tiny one in the case of the earth, extremely tiny. In fact, in the solar system the biggest precession is caused in Mercury, which is closest to the sun, and that is 43 seconds of arc per century, 43 seconds of arc, not even a minute, not even a degree, per century. But Mercury itself has an orbit that precesses of the order of 500 odd seconds of arc per century, and then of that 43 is the general relativistic correction, very tiny. Of course there are other systems where this is extremely pronounced. There is a binary pulsar which is like precessing 4 degrees per orbit, per rotation, per revolution. So this is because the masses involved are enormous, much greater. Okay. So this is the idea behind the lens vector. Now tell me how many constants of the motion are there. It looks like we have an embarrassment of riches. There is an h, there is an l, and there is an a. So there are 7 of these constants of the motion. The phase space itself is only 6 dimensional, they are not independent of each other. Yeah.
What that if r cross p points out to the board,
Yeah.
then if we take p cross l,
Yeah.
it's pointing out.
Yeah, the actual direction is along the aphelion or something like that. It is either out or in, but it is on this axis, it is on this axis. Incidentally, I could have changed the sign of k. It is true this constant of the motion has nothing to do with the k is positive or negative. So even if you had a repulsive potential, even if you have a hyperbolic orbit, there is still a Runge lens vector, there is still a lens vector of this kind. Huh?
Not always in the direction of the major axis.
Pardon me, it is always on that axis at all times, because if it is so at the 2 extremes of the orbit, it has got to be so at all times because it is constant. So you can find the direction of A at any convenient point in the orbit, and it is guaranteed to be the same at all times, just like the angular momentum is always normal to the orbit, normal to the plane of the orbit. So you have these 7 guys, but they are not independent of each other. You can quickly see that A squared can be written in terms of h and l squared. So once you tell me h and l squared, the numerical value of the total angular momentum squared and the energy, then I also tell you the magnitude of A. Moreover, you immediately see that A dot L equal to 0 is expressible also A dot L is 0. So one component of A is gone anyway, the one that is along the angular momentum. A lies in the plane of the orbit, just as L always lies normal to the plane of the orbit. So you really do not have that many independent constants of the motion. And the next question you can ask is, what is the symmetry group of this Hamiltonian? That is harder to discover, because unlike the oscillator case where I could identify J1, J2, J3 easily, this is harder because this A has a 1 over r term in it, and that is not an easy thing to handle. This guy is sitting here, these are not polynomials or anything like that. So in the next problem set I am going to give you A, and I am also going to tell you how to form combinations of A and L such that you have a simple algebra. It turns out that if you take suitable units and you take linear combinations of A and L, A plus or minus L roughly apart from constants, then you have 6 components for A plus or minus L, 3 for A plus L, 3 for A minus L, and these combinations would obey a certain Lie algebra. You can convert it to 2 angular momentum algebras, but not in A and L directly, but A plus L and A minus L, and that algebra is isomorphic to the algebra of rotations in 4 dimensions. So the symmetry group of this Hamiltonian, dynamical symmetry group, is SO4. This extra symmetry here translates in quantum mechanics to a degeneracy. So the moment you have symmetry, it implies degeneracy in quantum mechanics. It means there is a set of transformations under which the energy does not change. So a whole lot of states defined by different quantum numbers would have the same energy. So symmetry in classical mechanics goes over into degeneracy in quantum mechanics. And what is the degeneracy of the hydrogen atom? The principal quantum number is n, and what is the degeneracy of a state of the level specified by n? It is actually 2n squared, it is 2n squared, and the 2 comes from the fact that the electron has a spin and there are 2 internal degrees of freedom. So never mind the 2, there is an n squared still, and you have to explain that, and it comes about in the following way. It comes about because normally the state would be defined by 3 quantum numbers NLM of R, the wave function would be defined by 3 quantum numbers: principal quantum number, orbital angular momentum quantum number, and what is called the magnetic quantum number. This magnetic quantum number is the eigenvalue of one component of the angular momentum, say Lz or something like that. The energy levels E would also be functions of NL and M, but because it is a central potential, no single direction can be singled out, is special, and therefore the energy levels do not depend on M, but they would depend on N and L. And what kind of degeneracy would you have in that situation? Remember that in the Kepler problem, for example, n equal to 1, 2, 3 dot dot dot, L equal to 0, 1 up to n minus 1, and what does M do? M runs from minus L, minus of L minus 1, 0, L minus 1, L. It runs from minus L to plus L. How many of these states are there for a given L? 2L plus 1. So the normal degeneracy of the hydrogen atom would just be 2L plus 1 of a central potential. Any central potential, the energy levels would be specified by N and L, and for a given N and L it would be 2L plus 1 fold degenerate. But because of the Runge-Lenz vector, the hydrogen atom has an extra degeneracy which is called accidental degeneracy. It is not accidental, it comes about because of the nature of the 1 over r potential, and this too goes. So what is the degeneracy now? Summation m equal to minus L to plus L times 1, that many states, that was 2L plus 1, but now you also have to sum from L equal to 0 to n minus 1 of 1. So this is equal to summation L equal to 0 to n minus 1 of 2L plus 1, that is equal to n squared, that comes out to be n squared. and when you multiply that by 2 for the spin, then you get your 2n squared degeneracy. And of course the moment you depart from the 1 over r potential due to any correction whatsoever, this accidental degeneracy disappears completely, it is lifted and you have a splitting of the levels. This is the reason why in the hydrogen atom the 2s level and the 2p level are not the same, whereas if you strictly had just pure 1 over r potential, 2s and 2p you should not be able to distinguish between, no L dependence, but you actually have a difference due to what is called the fine structure. So you learned this in quantum mechanics, but let us get back to classical mechanics. But I want to point out to you that the origin of this whole business is in this extra symmetry, this dynamical symmetry for the Kepler problem. Okay. So as you can see, it is not easy to find the dynamical symmetry group of a problem, of a particular integrable problem. Okay. Yeah. Yeah. I would like to switch stream a little bit and go on to several other things I wanted to talk about, but first, any questions? What we have done so far? Yeah. Yeah, what I am going to do is to give you a problem sheet in which I will write down the specific generators and ask you to check out the algebra. So this involves putting in all the constants and so on, which I will do carefully. I'll give this both for the isotropic oscillator in 2 and 3 dimensions as well as the Kepler problem. So I will write this out in as a form of notes and give it to you. Yeah.
So
yeah.
You have 5 constants of them.
Pardon me?
We have 5 constants.
Yes.
We need only 3.
You need 3 of them which are independent of each other. So it is clear that you do not have that many that are independent of each other. They have to be functionally independent and they must be in involution with each other. These guys are not in involution with each other. Which 3? H, L squared and L3 for example, that will do, that is it. The Poisson commutator of the Poisson bracket of Li with Aj is not 0, that is exactly what the algebra is going to be, that is not going to be true. So they do not commute with each other. Yeah.
How are the generators used in, once you write down the generators, what
Yeah.
do
What you do with that is, okay, this really takes me into group theory. I really at some stage we should come to terms with this, and I should define for you what a Lie group is, what the role of the generators is, and how you generate the elements of the group from the infinitesimal generators. So probably this would be the best thing to do. Let me devote an hour to this separately. I'll start with the rotation group and do this because it is very, very useful. How many people here have had a little bit of exposure to group theory? Okay, then it is important, then let us do that, let us do that since the majority has not had it. So let me do that. We have 15 minutes today, so let me do the following, not waste this time. I will talk about generators and the symmetry group a little more because we need to slowly move into statistical physics, and the way we are going to do that is by asking what happens when integrability is lost, how does chaos set in, and then what happens after things become irregular and so on. But before I do that, let me fruitfully spend the remaining time today by going back a little bit and showing you how the Lagrangian framework as well as the Hamiltonian framework and our framework of stability analysis is useful in analyzing a problem with constraints. So let us switch streams and do this, and let us look at bead on a rotating hoop of wire. I promised I would do this long ago but never got down to it, so let us do that problem now right away, and it will help us revise all that we know about the Lagrangian and Hamiltonian framework. So let us do this quickly. Let us suppose I have a vertical hoop of wire, a circular hoop of wire. Let us draw the circle first and then put the axes. a vertical circle, there is gravity acting downwards, let us call that the z axis, and let us call this the y axis, so x comes out of the plane of the board. I have a right handed coordinate system. To start with, the circle, the hoop is in the yz plane, and I put a little bead on it of mass m with gravity acting downwards. I am going to assume it is frictionless, I am going to assume that this bead moves smoothly and frictionlessly on this wire. What is the Lagrangian? This guy, and I will assume the potential energy to be 0 here and mgz as you move upwards. So this Lagrangian is T minus V, and this is equal to 1/2 m x dot squared plus y dot squared plus z dot squared minus mgz, and there is a constraint in this problem, and the constraint is that the bead is sitting on this hoop of wire at all times. So we need to know the equation of this wire, and this wire has this hoop has a radius r, and it is here, and what is the equation to this hoop? It is a circle in the yz plane, and therefore and the circle center is at y equal to 0, z equal to r, so it is y squared plus z minus r whole squared equal to r squared. Okay. So in principle I can eliminate z in favor of y. Now I would like to make matters interesting, this is an elementary problem. One thing is to find out what is the period of oscillations of this. Would that be simple harmonic? In general no, except for very small oscillations near the bottom of this hoop, it is not going to be simple harmonic. But let us make matters interesting by saying that this is actually rotating with some uniform angular speed omega. The moment I set this rotating, I have now cylindrical symmetry about this axis or axial symmetry. So what coordinate system should I choose? Cylindrical polar coordinates, right? So let us choose cylindrical polar coordinates, and let us use rho, phi and z. Rho squared is x squared plus y squared, phi is equal to tan inverse y over x, and z remains as it is. What is the kinetic energy in these coordinates? So I should erase this, right? What is the kinetic energy in these coordinates? Well, rho dot squared certainly plus rho squared phi dot squared plus z dot squared minus mgz, this fashion. So this is certainly true, but then z is related not to y now, but remember it is rotating, so it is actually related to this axial distance, which is x squared plus y squared or rho squared. So the constraint is really z minus r squared is rho squared here, which is x squared plus y squared, because that is the distance of this point from the z axis, square of the distance from the radial distance, axial distance from the z axis. Okay. But phi dot is omega, because the rate at which this azimuthal angle changes is fixed by u. You are rotating this hoop at constant angular speed, so we can in fact get rid of this 2, write this as omega squared, because phi dot is always omega. Now let us remove, the whole point is there is a lot of rho dependence here, let us remove the z in favor of rho. So let us solve for it, and you get z minus r whole squared is equal to r squared, or z equal to r plus or minus square root of r squared minus rho squared. There are two roots, and what do they correspond to? Well, it says there are two possible values of z for a given rho. So if you are here at this value of rho, there is this root and this is this root, one above this halfway point and the other below. We are interested in motion here. So which root should I choose, the plus or the minus? I should choose the minus. I should be very careful to choose the minus. You sure the minus is what I should choose? Because if rho is 0, I better have z equal to 0, which corresponds to this point, otherwise it would go there. So I should choose the minus sign. Minus. Therefore what z dot? It is equal to minus 1 over twice square root of r squared minus rho squared. Then I have to differentiate minus rho squared, which is equal to minus 2 rho dot up there, and the minus signs go away, the 2 goes away, and I have rho dot over r squared here. So let us put this in, and I have L equal to 1/2 m rho dot squared plus z dot squared, which is rho dot squared over r squared minus rho squared, plus 1/2 m omega squared rho squared minus mg and z, which is plus mg square root of r squared minus rho squared minus mg r. Okay. And I can simplify this, right, r squared, so it becomes m r squared over r squared minus rho squared, because this rho squared cancels. What is this L a function of? Rho and rho dot, that is it. So how many independent degrees of freedom are there now left? Why do you say 2? What are they? Is it 1 or 2? I would say just rho, I would just say rho, everything else is gone. I know how phi changes, phi is equal to omega t plus a constant, and I know z in terms of rho, so there is only one degree of freedom rho and a corresponding velocity rho dot. So it is a problem which is really one dimensional. So this L is a function of rho and rho dot, that is it, just a one dimensional problem, but a fairly difficult kinetic energy. This is the kinetic energy part, but there was another part which came out of the kinetic energy which does not involve a generalized velocity, except that the velocity has gone, it has disappeared, it has gone here in omega. Now what does this look like to you? It looks like a potential, it looks like an oscillator potential, rho squared in this radial coordinate, but remember L is t minus v, so it should have looked like minus half rho squared, except it looks like a plus, looks like a plus. So it is like an oscillator potential, but an inverted oscillator potential, it is trying to push you away. Now what do you call this tendency when you rotate something it pushes you away? It is the centrifugal term, this is the centrifugal term. So you see what is happening is not only that constraints have been taken into account automatically, I have not put in any constraint force, I used that equation and got rid of z, but a non-inertial force is also put into, is also included automatically. Yeah. Yeah. Yes, certainly they are. Yeah. No, I am saying rho is the degree of freedom, rho and rho dot are the pair of dynamical variables. A degree of freedom is just a coordinate always. but I need a degree of freedom, a generalized coordinate as well as a generalized velocity or a generalized momentum. So I am very carefully distinguishing between degrees of freedom and dynamical variables. Dynamical variables come in pairs, they are the degrees of freedom or the coordinates together with the corresponding velocity or momentum, depending on whether you are looking at the Lagrangian or the Hamiltonian. So what all I am pointing out is that we have got rid of all the other, we have got rid of phi, we got rid of z, we are left with rho. Phi dot has been put equal to omega, a constant, and z dot has been expressed in terms of rho and phi dot and rho dot, and here we are. So now I could write the Euler-Lagrange equations down. There is just one equation to write, and that is got for the delta L over delta rho equal to etc. But let us go and do the Hamiltonian. And what would you do? You would first start by defining a P sub rho, the momentum conjugate to rho, the radial momentum, as equal to delta L over delta rho dot. And what is that equal to? That is highly non-trivial. It has this term, this whole mess here. So this is equal to mr squared, and there is a 2 rho dot, so the 2 cancels, rho dot over r squared minus rho squared. Since there is just one degree of freedom, rho, let me not write this subscript here, let me just call it P for ease of notation. It is the momentum conjugate to rho, and the next step is of course that you must write this as rho dot equal to P times r squared minus rho squared over mr squared, and then you must find the Hamiltonian, which is a function of rho and P, equal to P rho dot minus L. But you must be careful to remove all rho dots on the right hand side and express everything in terms of P and rho, and that would be a Hamiltonian. So what happens next is we have H of P and rho equal to, and we could write this down immediately. If I do this rho dot squared here, it is going to be P squared, so let us do that, it is a painful thing, but P rho dot is P squared r squared minus rho squared over mr squared. That takes care of the P rho dot term minus this term, in which rho dot is replaced by that formula there, and as always happens in this case, just as half mv squared became P squared over 2m, you are going to end up with just a factor of 2, here, just half that, minus the rest of the Lagrangian. So minus 1/2 m omega squared rho squared minus mg square root of r squared minus rho squared plus a constant. I am not interested in the constant, mgr is just a constant. That is the Hamiltonian. Okay. Now let us write down the Hamilton equations, and then I am going to leave the rest of it for you to do. So rho dot equal to delta H over delta P, and that is guaranteed to be this, P times r squared minus rho squared, nothing new. But what is P dot? That is minus delta H over delta rho, and that is equal to, now things get interesting, you have to first differentiate this term and put a minus sign, so it is equal to P squared rho divided by mr squared. Because I differentiate, I get the minus 2 rho, the 2 cancels, the minus goes away, so it is this term here, and then I differentiate this with a minus sign, so plus m omega squared rho, and this is plus mg over twice root r squared minus rho squared minus twice rho, so mg rho with a minus sign. These are non-trivial equations. You have to solve these two equations, and they are fairly non-linear, as you can see. Where are the critical points? where would the critical points be? First we have to ask physically, does it make sense? If you started at this point and whether you rotated it or not, nothing is going to happen. So P equal to 0, rho equal to 0 must certainly be a critical point, and that is certainly true. If I set P equal to 0, this goes away. If I set rho equal to 0, this goes away. Whole thing goes away. Notice that rho cannot be equal to r, that is not a critical point, because then this blows up. So the only possibility for this thing, the only way it can vanish is if P is 0. Now what I want you to do is to look at the critical point at P equal to 0, rho equal to 0, linearize about this point and ask what happens. Linearize and find out whether it is what sort of critical point this is, stable, unstable, etc. Is there any other possibility? Actually there is one more possibility, and the possibility is if P is 0, this side is 0, this term goes away, then this could vanish independently, and it may have a root other than rho equal to 0. It may have a finite root provided it is real. Now I leave that as an exercise to you to complete, and we will write down the solution tomorrow. If you look at that term, it will turn out that if omega is sufficiently high, then there is a possibility that you have a non-trivial rho. That means there is some distance here depending on the speed omega which is stable, and then at that point this guy will become unstable and the bead will move out and remain at that point. So the oscillations would be about that point, and what is called a bifurcation will happen. Once a critical value of this angular speed is reached, in this problem it will be something like square root of g over r or something like that, then you would find that the stability changes. The origin becomes unstable and a new stable point becomes a new critical point becomes stable, and we will look at this tomorrow and complete the rest of it. So stability analysis is going to help us to interpret the solution, and this problem displays an example of what is called a bifurcation. A small change in the angular frequency omega in the vicinity of a critical value, either this side or that side of it, is going to cause a large qualitative change in the behavior of the dynamical system. So this problem also serves to give you an example of a bifurcation in a dynamical system. Now once you do that, then of course you can change the shape here and ask what is going to happen, etc. Tell me physically what is going to happen if I start rotating this with infinite angular velocity, arbitrarily high angular velocity. What do you think will happen? Yeah, it should go and stick here. That should be the solution. So already you expect that this rho, which is the stable value of rho, once you exceed a critical point, should go and stick there. So in fact we can anticipate ourselves and write what is rho equilibrium or steady state as a function of angular speed, and if you do this you discover it is the origin here up to a certain angular speed, and then at a critical value it is going to take off and then saturate to the value r. So what would this curve look like? We do not know yet. It might do this, it might do this, it might start with a finite slope and go there. It is of great interest and importance to find out exactly what does it do at that point, and we will discover that this threshold behavior is like a square root singularity. So it is perpendicular slope here and then it goes and saturates in this fashion. It is characteristic of what is called a pitchfork bifurcation. So as you can see, even this very simple looking problem, you do not really have to solve the entire problem, but we can understand completely what the dynamical system is going to do by this combination of techniques, the Lagrangian followed by this stability analysis. It is going to take care of this. So let me stop today.